In the last video, you have learned how to deduce the structure of the molecule if molecular formula and the spectra were provided to you. Let us say today how to deduce the structure of molecule when spectral data has been provided but no molecular formula has been given. So the first step involves fetching of molecular formula. To derive the molecular formula, let us use various spectral data one by one. In a mass spectrum, molecular ion peak appears at m by z 158. The IR spectrum shows absorption at 1740 centimeter inverse, which indicate carbonyl stretching frequency of ester. 1170 and 1150 centimeter inverse indicate CO stretching frequency. In H1 NMR, number of hydrogen has been given. So let us count the number of hydrogen. 6 plus 3, 9, 9 plus 3, 12, 12 plus 2, 14, 15, 16, 17 and 18. So total number of hydrogen becomes 18. C13 NMR exhibit total 8 signals, out of which the signal at 22 is found strong in intensity. So maybe 2 carbons are present over here. So total number of carbon becomes 9. With this information, molecular formula becomes C9H18, which gives the molecular mass 126. While the given molecular mass of molecule is 158. So 158 minus 126, difference is 32. And as you know, the atomic mass of oxygen is 16. So just by adding 2 oxygen, molecular formula becomes C9H18O2. With this molecular formula, let us try to extract the information from H1 NMR data. First signal appear at 0.81, which is a doublet for 6 proton. So doublet means the neighboring carbon should carry single hydrogen. 6 hydrogen are there, so it can be 2 methyl groups attached to the CH. Next signal at 1.25 delta, again it is a doublet for 3 proton, so methyl should be attached to the CH. Next signal 1.3 delta, which is a triplet for 3 hydrogen, so methyl should be attached to the carbon which carries 2 hydrogen. 1.6 delta shows a triplet with 2 hydrogen, so it is CH2 attached to the CH2. 1.83 is multiplet for single hydrogen. Time being we will write the CH, but there can be a number of neighboring hydrogen. 2.5 delta shows a sextet for 1 hydrogen. So we have 1 hydrogen and neighboring carbon should carry total 5 hydrogen. So it can be a CH3, CH and CH2. Most d signal appear at 4.2 delta, which is a quartet for 2 protons. 4.2 is very much d-shielded, and as per molecular formula, oxygen is most electronegative. So this carbon should attach to the oxygen, and being it is a quartet, neighboring carbon should carry 3 hydrogen. So the partial structure become a ethoxy group. In H1 NMR data, almost all the signal shows the same coupling constant, which is J is equal to 6 Hz. So it is difficult to find out the coupling partner. To get the information, we will take the help of cozy correlation. Let us read the data. 0.81 signal correlates with 1.83. 1.83 correlates with 0.81 and 1.6. 1.6 correlates with 1.83 to 2.5. 2.5 correlates with 1.6 and 1.25. So we can have the connectivity 0.81 connect with 1.83. 1.83 has a correlation with 0.81 as well as 1.6. 1.6 correlates with 1.83 and 2.5. 2.5 correlates with 1.6 and 1.25. So this is one spin system. Another spin system has 1.3 correlates with 4.2. So there are two spin systems. Based on this information, we will find out part of the structure. 0.81 correlates with 1.83. So 0.81 we have the two methyl groups which is correlating with 1.83 which has the single hydrogen. So part of the structure is isopropyl group. 1.83 has a correlation with 0.81 and 1.6. So 1.83 which is a methine group will have the connection with 1.6. At 1.6 we have the methylene group. So let us write the methylene as it is a triplet. One hydrogen is already there. So next carbon should carry one more hydrogen in order to get the triplet multiplicity. Further, 1.6 is correlating with the 2.5. At 2.5 delta, we have the sextet for one hydrogen. So it should be a methine. And as it is a sextet, the neighboring carbon should carry 3 hydrogen. So the methyl group should be attached with this methine. So part of the structure is shown here. Based on this data, the CH shows a multiplet because it is coupling with 3 plus 3 plus 2, total 8 hydrogen. So at 1.83, the signal appears as a multiplet. At 2.5, the signal is sextet. So neighboring carbon should carry total 5 hydrogen as shown in a part of the structure. Next spin system is between 1.3 to 4.2. At 4.2, we have the methylene and it is correlating with 1.3. So at 1.3, we have the methyl. So this also confirms the presence of ethoxy group. With these two fragments, let us calculate missing part over here. Molecular formula is C9H18O2. So far, we have taken care of 8 carbon, 18 hydrogen and 1 oxygen. If you do the subtraction, left behind with the 1 carbon and oxygen. As you may recall from the IR, we have confirmed the ester functionality. So the missing component is a carbonyl group of ethyl ester. So let us connect this carbonyl with these two fragments and obtain the structure of the compound. We confirm the structure of compound by observing C13 and het core data. C13 NMR shows total 8 signal. The signal at 22 delta is strong. So 2 carbon can be present at 22 delta. Signal at 176 indicate carbonyl carbon of ester group. Let us look at DAPT1 for 35 data. It shows a positive signal at 14, 16, 22, 26 and 38, which indicate there can be a CH3 or methine carbon. DAPT135 also indicate 4260 signal as a negative signal. So two methylene groups should be there. From head core, we can establish the correlation between 1H and C13 signal. We can use this signal for correlation with carbon. The structure with hydrogen assignment is already given. So let us correlate this hydrogen with the carbon. 0.81 correlates with 22. So we have assigned signal 22 for this methyl. 1.25 correlates with 16. So we can assign this methyl to 16. 1.3 signal correlates 14. 1.6 signal correlates 42. 1.83 correlates 26. 2.5 hydrogen correlates with the carbon, which is at 38, and 4.2 hydrogen correlates with the 60. So in this way we can establish correlation between an carbon and hydrogen which are bonded by single bond. Further, the structure can be confirmed by analyzing fragmentation pattern given in a mass spectrum, as fragmentation pattern act as a fingerprint for a specific compound. We found out ester compound. So in ester, two cleavages are common. Alpha cleavage, where the bond between carbonyl carbon and oxygen undergo homolytic cleavage, giving asylum ion at M by Z 113 with removal of ethoxy radical. In second alpha cleavage, the bond between carbonyl carbon and carbon undergo homolytic cleavage, giving alkyl radical, and asylum ion will appear at M by Z 73. From this asylum ion, carbon monoxide can go as a neutral molecule, giving the alkyl cation at M by Z 85. Second type of fragmentation which occur in esters is through the McLafferty rearrangement. For this compound, McLafferty is possible with alkoxy side chain as well as alkyl side chain. Let us see McLafferty through alkyl side chain. McLafferty rearrangement has characteristic transfer of hydrogen from gamma carbon to oxygen. It involves 6-member transition state with the cleavage of alpha beta bond. The first McLafferty gives odd electron spaces at M by Z 102 with elimination of isobutene. Let us look for the second McLafferty which occurred through a alkoxy side chain with elimination of ethylene, and odd electron spaces appear at M by Z 130. Other fragments in a mass spectral data can be shown by cutting isopropyl radical, methyl radical and ethyl radical, giving the fragments at M by Z 143, 129 and 115. Thus, along with the mass spectrum, IR, NMR and 2D NMR data provides the structure of molecule more precisely.